Thanks, Cassie. And just to let you know, it sounds like from what Cassie was telling me in the audience, there's a number of you that may be familiar with some of these concepts. So there are some things that I may go over kind of quickly on and to get through some more of the design examples at the end. But certainly, if there's something you feel like I'm going too fast on, stop me and I will be glad to answer any questions. Okay, so what we're going to cover today is the unified sizing criteria a little bit, and specifically talk about how we can use multi-stage outlet design to address especially some of the smaller storm aspects of the unified sizing criteria. So here you just see an example of some of the elements of the unified sizing criteria that are identified in the Iowa Stormwater Management Manual. There are the large storm aspects, which a lot of us have been familiar with for many, many years, where we try to address control flow rates to protect against flooding. But then there's the small storm aspects that are out there too, that focus on managing the storms that come on a more frequent basis. So these are the recharge volume, which is focused on the smallest of storms. Not every community has a recharge volume standard, but some have set it at like a half inch, 3/4 of an inch. There are some that are 1 inches. But basically, you're trying to actually capture that water and infiltrate it or reuse it to actually reduce the amount of runoff that's generated. Sometimes this is accomplished through just soil quality restoration, but there are some other practices that can be done as well to meet that standard if your community has it. Then there's the water quality standard, which focuses around 90% of the storms that happen in Iowa. And that's about 1.25 inches of rainfall depth across the state. So having practices that capture, slow, filter, and provide basically water quality improvements. The goal is, or one of the primary goals is to try to reduce total suspended solids by about 80%. If we're achieving that goal, then we usually are achieving other things like nutrient reduction and bacteria reduction and things like that as well. Various practices are better or worse than that if there's a certain pollutant you're really caring about. But that's kind of the general idea behind the water quality standard is to capture and treat those most frequently occurring storms, and then also the first flush of some of the larger storms. We focus on that 1.25 inches. We generally accomplish those goals. And then multi-stage outlets is especially applicable to what we talk about is the channel protection volume. And I'll get into that in a little more detail in a minute, but really managing the water from that storms that happen about once a year on average, which is about, between 2.5 and 2 3/4 inches of runoff or rainfall. So 2.5 to 2 3/4 inches of rainfall across the state is basically that storm event. And why is the channel protection volume aspect of the unified sizing criteria so important? This is an analysis that many of you have probably seen before. Mike Perez did this while he was at Iowa State University. He looked at an area of Ankeny that was developing. At the time, it was about 42% impervious, so there are still some parcels you can see that were yet to develop. So probably upon full build out, we're probably getting closer to 50%. But they looked at it at the time of development was about 42% and did an analysis of, well, what would we look at for runoff from this type of an area? And what they found was some pretty substantial changes to hydrology and the way water runs off the landscape, especially for these smaller, most frequently occurring events. You see, if we look back to the natural condition that happened, before there was any even agricultural development, back at the prairie, we would have seen very, very low flow rates and volumes. With the development of agriculture, a substantial increase in flow to that level. But then once we get up to the developed condition without any kind of stormwater management, we're talking, flow rates that are 14, 15 times higher than the natural condition and that are about 3 times as large as the existing agricultural conditions. So, and then in addition to that, we're seeing, a 20% increase in volume as well. So we have higher volumes of flow that we need to think about. And then also the rate of flow is tripled. So we're extending, even if we do stormwater management, how do we do so in a way that doesn't cause downstream channel erosion. And in the past, when we've just been managing for larger storm events, we typically allow a lot of those larger flows to just leave the basin rather rapidly, which would open up for the potential of channel erosion. And unfortunately, it's not hard to go out and find examples of this condition. Almost any urban waterway that you walk through, unless there's been more recent kind of management that controls these smaller storms, you tend to see things like this. So very, very rapid channel erosion behind homes. This was in a subdivision that was developed only in the early 2000s. I think an upstream area developed in the very late 1990s. So it only took 10 or 15 years for this stream to go from something that you could walk across to something that looks like this. Another area with some substantial erosion behind a house that was starting to wash away a retaining wall. This is a recent project that I'm actually working on right now that we're doing stream restoration in here, where again, we hear the stories of people saying, yeah, I used to be able to step across this stream and now it's 15 feet deep and 30, 40 feet wide right behind people's houses because of these changes in hydrology. Again, more rapid widening of the stream. Again, these are all very small watershed examples, anywhere from 100 acres of drainage area to 300 or 400 acres of drainage area. Infrastructure that's imperiled. We see here a trunk sewer that's exposed by some of the erosion, and a sanitary manhole here. And this is an area where later on, about 2-3 years after this photo was taken, we had a series of 3, 4, 5 inch rainfall events that happened 3 consecutive nights. It ended up washing out the sewer. That basically flipped one of these manholes on its side, exposed the sewer to the creek, and then there was an emergency repair that had to be done. More very powerful scour erosion downstream of this outlet pipe. And again, another story here. Public Works said when this area developed in the late 1970s, this was the stream that was about 2 feet across or 2 feet deep, a couple feet across. And now it's something you can step across. And now again, 15 feet down, 40 feet wide. This photo was taken back in 2009. So the city has actually come in since then and done a couple different stream projects here to try to address this erosion. And this all kind of falls in line with a number of studies that have been done that look at the channel evolution model, where basically once that hydrology changes, the stream's going to react to it. You have this historic cross section where the stream is like used to basically accommodating a certain base flow. That basically channel protection event is kind of about the similar of what we would typically call a bank full event in natural channel design, which is basically about a 1 to 2 year storm event. That typically is what your stream wants to develop a cross section to handle. It will convey that flow in the stream channel. And then usually you have a well-connected floodplain where once it gets above that, 1.5 to 2 year storm, the stream could actually start to spill out into that floodplain. That allows the velocity to drop. It reduces the amount of shear that you have. And that's all what we would like to see in a good condition. However, once the hydrology starts to change and that 1 to 2 year storm peak rates increase, the channel starts to react to that. It starts to be able to convey more of the soil particles. It starts to be able to mobilize more of the larger stone materials, and it's going to widen and deepen over a very short period of time. So again, you can see how over time, in this example, the channel just gets wider and deeper to eventually it gets an ultimate cross section that reaches a new level of equilibrium. But that could take a few decades for it to kind of play out. And at that point, how much soil has been lost, but also is there infrastructure, is there property that is in peril now because of those changes? And as part of these studies done by the Center for Watershed Protection, they looked at hundreds of different watersheds, especially in the eastern United States, and different levels of development. And they were able to chart out, based on impervious cover, how much channel widening they were able to see, which is this enlargement ratio, which is basically the cross-sectional area of the stream before development and then how it changed over time. So what you're able to see, for some reason, see if my annotation is going to work here. I can't get my annotations to work now for some reason. But basically, oh, here we go. Basically what you see is, as this chart, as we're moving upwards on the x-axis, we see impervious cover. On the y-axis is that enlargement ratio. So when we get to 40% impervious, which a lot of our suburban areas are somewhere between 30 and a 40% impervious, especially in single family areas, you can see that enlargement ratio typically is about 4 times. So that cross-sectional area of kind of the stream channel, 4 times larger after development as before. And then when we get into even higher levels of development, you can see those enlargement ratios increase. When you get to 60%, we're up into that 7 to 1 ratio. So something that's been extensively studied. It really shouldn't be a surprise when we see these like smaller storm changes that we see the streams react this way. And unfortunately, it can cost a couple $1 million a mile to come in and really restore some of these streams that have been impacted in this way. So if we can start to think about that ahead of time and provide some management from that when development is happening, we can stop these problems from spreading and being multiplied. So now we start getting into some of the design and thinking about, well, as designers, how do we deal with this? When we're proposing new projects, I always try to recommend to people do some preliminary design work early in your project, do some preliminary sizing. If you figure out what you're going to do for your development really early on and then try to squeeze in the stormwater management at the end, you usually end up having to cut out things you want. You have design layouts that aren't as efficient. So if you start from the beginning with an understanding, well, how much area do I need to devote to stormwater management? You're more likely to have a more efficient design and have less things that are lost. You can settle that basin where it belongs, have it fit into the landscape better, and shape your proposed improvements around that. So there are some equations in the stormwater manual in section 902 that talk about preliminary design and estimating storage. This equation can look a little scary with you've got things to the second and third power, but it's really not that bad if you import it into a spreadsheet. What this is basically just telling you is your ratio of outflow to inflow, which is QO over QI, goes into this part of the equation, and that allows you to solve for the ratio of the expected storage you will need to the volume of runoff you're actually getting from your area, from your development. So usually a lot of times our outflow inflow ratios, outflow is set by some sort of allowable release rate based on local standards. Your inflow rate is going to be the developed rate of flow coming off after development is fully complete. By dividing those two figures, you get your outflow inflow ratio. Then you plug that into the equation up here. It gives you that ratio of storage to runoff. And then by knowing your runoff rates from your models, your runoff volumes from your models, you can then calculate, you basically can just multiply that out and get how much storage you need. And what I typically have seen using this method is sometimes it underestimates the amount of storage you might actually need. So I usually recommend adding about a 15% correction factor to that just to account for those kind of effects. So if you basically know how much storage you need, then and I kind of drew on some of the screen. Basically, if you know the outflow rates and then you know your inflow rates and volumes, again, you can calculate the storage. Where do you get this information from? Well, your natural condition, and in some cases, this may not be necessary anymore. A lot of our communities are having to remove the natural condition as a requirement to look at for release rates. That's due to Senate File 455 that was passed this year. However, you as a designer, certainly maybe you make that an internal goal. And I would still say that there's some benefit to looking at natural conditions, especially for those storms that are from the 2-year to the 50-year. The new standard in Senate File 455 basically says you need to control release rates to the existing condition from the 5 to 100-year events to no greater than the 5-year existing. That's not a statewide requirement. That's just saying cities that's the most that they can mandate for those larger storms. However, that just means basically you're setting one release rates for everything from the 5 to the 100-year. So sometimes using that natural condition is a good way to figure out what your release rate should be for the 5 to 50 year storms. But again, cities can't require that, but it's probably a good metric for designers to use. Um, Mimicking natural hydrologic conditions certainly has a lot of benefits, even for those larger storms. So if you're using the natural condition as a standard, you can do those calculations. The existing condition is what most communities are kind of moving to now. So you need to really evaluate what the existing conditions are as far as uh, the level of impervious cover and time of concentration, things like that, to determine what that existing flow rate is off your site. And then your developed condition, what are you actually proposing to be designed? What are its conditions? That's where you get those flow rates. You develop models for those. Usually a TR55 model will give you that information. It'll give you the inflow rates to your basin. You'll use it to calculate your outflow rates to your existing conditions for your outflow rates. For the small storm, though, we pivot a little bit, and we need to calculate the release rate for that smallest storm. And this is where you go to section 302, which is a small storm hydrology chapter. There is a chart and a formula in there that helps guide you through how to do this. Basically, you need a few pieces of information. You need to basically know how much runoff volume you have, and you need to convert that into watershed inches. That goes into this formula that allows you to calculate the unit peak discharge. There are certain software programs that actually may give you that information up front. So if it calculates it for you, you don't have to do this equation. But if for some reason it doesn't, you basically take your peak rate of flow, you multiply it by these conversion factors to get the unit peak discharge. Then you'll take this number, the 978 in this example, you look at your chart, you go to the x-axis, find 978, you draw up to the curve, and then over to the left to find that allowable inflow-outflow ratio, that QO, QI, which is what we were just talking about in some of the previous slides. And in this example, it's about 0.03. So that's telling us our outflow rate needs to be about 3% of what our inflow rate is. So for an inflow rate of 106 CFS in an example, you multiply that by 0.03, your allowable release rate will be 3.2 CFS. So that's how we calculate the allowable release rate to meet the channel protection volume standard. So if you plug that into this formula here and work your way across, this starts to give you an estimate of how much storage you're going to need to manage the 1 year storm. And then with Senate File 455, we're going to focus a lot more on the 100-year storm and the storage you need for that. So again, with these changes, what is our allowable release rates? Before Senate File 455, you might have seen communities requiring natural levels be used unless the 5 year existing was more restrictive. So it could have played out a little bit more like this, where you had a variety of flow rates to look at for different storm events. Now we're really looking at, probably, again, I would say designers could certainly continue to look at those things. I would advise you to look at those things. But as far as what may actually be required, you may be looking at more of the smaller storm and the larger storm, and really anything in between here for probably the 5 to 50. Some communities may still set a 2 year standard, but anything really between the 5 and the 50, um, it's going to be less than 95, because when you design something to manage the 100 year storm, you're just going to end up releasing less than that at some level when you control the smaller storms. But without having an actual set standard for those smaller storms, it could be larger than some of these allowable release rates would have previously provided for. And this, again, this estimation, just to clarify, really we're just looking at what we call a live storage, which is above any permanent pool you have, or if it's a dry basin, it's all live storage. But we obviously don't count any of the quote unquote dead storage, which is the normal permanent pool, when we're making these estimations. So usually what I do is look at the stormwater manual and say, well, we'd like to like limit our bounce to reduce erosion potential. We'd like to keep things for the smaller storms, the 1 year storm at about a 2 to 2.5 foot level of bounce. That helps establish that vegetation better. If you have water that's getting 4 or 5 feet deep once a year, it may be more difficult to maintain the basin and provide keep the vegetation going and to not have it be eroded away on the shoreline. And then for safety, you may want to set some sort of high water limit, 5, 6 feet, what have you, to figure out how big your basin should be. So if you do some just rough back of the envelope calculations to do some initial sizing, if we know what our storage for the 1 year event's supposed to be and divide it by two, that means, that if I was going to draw on a plan, a contour that's about 1 foot above what I expect my normal pool to be, I'm going to need about this much area to provide that much storage. So I would probably start drawing a shape that has about 134,000 square feet in this example for my basin. And then I start, maybe you start setting some contours away from that or just doing some rough approximation of what the side slopes would be. You want to make sure for that 5 to 6 foot deep level that again, you're going to have enough storage. So you're looking and making sure maybe that upper limits of the basin, maybe it's going to be about 180,000 square feet in this example. And a lot of times, it depends on the size of the site you have. Smaller sites, it might be more like 10% of your site area, maybe even a little higher, depending on how impervious it is. As sites get bigger and bigger, it seems like that these start to trend down to maybe like 4 or 5% of the overall site area. And again, it depends on how much impervious cover. That would be for like a more natural, single family development might be more 4 or 5%. If you're more commercial or industrial, higher levels impervious, maybe it's going to be 6, 7, 8% for things that are about 40 acres or larger. So, and again, this is just mainly sort of before you start really getting into the details of the design itself, making sure you have the right amount of space on a site. So that it's not just squished in there and we've got the right amount of room to begin with. Once you get into final design, you kind of refine how the actual outlet structure is designed. Again, following kind of that same design example, we calculate our allowable release rate. We start to develop a grading plan where you figure out your contour area and the elevation of the basin and making sure, that what your new grading plan is above what our estimate should be. It's always a little easier to shrink it down later, than try to make it bigger. Then we look at some of those higher elevations, making sure that, by the time we get to the top of the basin, we have enough storage for what we think we're going to have. At this point, it's probably a good time to check in and look at, say, well, especially if you're doing a wet pond, is it getting to the point where this pond is big enough that it's going to need a state permit? So checking, looking at how much you're storing, what the height of the dam is, and seeing if because if it is a state permit, there are some different standards and requirements that you may have to follow depending on what hazard classification it has. So a good time to check in for that. And then you start getting into actually designing this outlet structure. So, you're in this case, we're really focused on two specific storm events. We're looking at the release rate we need for the 100-year storm on the left. Usually I'd like to do that first. I'd like to figure out what is my biggest pipe going to be. So we do a quick little, if we have an idea of what the elevation of the flow line of your outflow pipe is and the high water of the 100-year, you can start to do some calculations and get an idea of, well, how big of a pipe do I really probably need to pass that 100-year flow? And in this case, it works out to be about a 36-inch diameter pipe. And then the second step is, well, what about my low storm, my small storm orifice or control? What will I need to control that channel protection volume? You can do the same thing. Your allowable release rate for this example was 3.1 CFS. And if we're trying to maintain a water level of about 2 feet of bounce, again, you can kind of rearrange the orifice equation to get an estimate of how much what size you're going to need. In this case, it works out to be about 9 inches. After that, you actually have to put this into your modeling software, whether it's HydroCAD or HydroFlow or different other software packages, where you're actually putting your actual stage storage volumes in there and your actual design and try to iterate. The equations I just showed you were good for an initial estimate, but you have to kind of make sure that things work out. And you may have like different stages. So we're going to have our lower stage or our primary stage for the 100-year control, our lower stage for to control the 1-year event. But then once it gets above the high water of the 1-year storm, we're going to need some other way to get water in the inlet. And these could be weirs over the side of the structure, like if it doesn't have a top, or it could be like an area intake with openings on the side that allow water to get in this outlet pipe. And I'll show some illustrations of that here in a minute. This just kind of breaks it down, but it's a little bit of an iterative process. You may have to go through a couple design iterations to get to your final design, but ultimately your goal is to make sure that during a 1-year storm event we're meeting our allowable release rate, that it's less than what's allowed, and then the high water level is kind of staying in the range we want it to be in. For the 100-year event, same thing. We want to make sure that our allowable release rate is less than what's allowed, or our actual release rate is less than what's allowed, and that our high water level is getting to the level that the designer is comfortable with. And again, now with Senate File 455, probably these smaller storm events, are just going to fall in line because the high water controlling the 100-year, as the water level isn't going to be as high, you're not going to push as much water out for those smaller storms. If Senate File 455 hadn't been passed, we'd be doing some other steps to kind of check some of the flow rates for these more moderate-sized storm events to make sure these different weirs in here control those smaller storms appropriately. Different like opening sizes, things like that, elevations. Once you've done this, it's always probably a good idea to check your velocities at the outlet. In some cases, you might actually want to upsize that outlet pipe and then put an orifice plate in so you can keep controlling the flow the way you want, but like get the flow down to a manageable velocity at the outlet for scour protection. Either that or you're going to have to just armor up with higher levels of armor at the outlet. So there's just some things we typically see and how these work out when you do the design calculations. You might just have, if you really aren't caring about like channel protection and volume at all, but you're wanting to manage more of the moderate or kind of middle storm events, you might see a more dry detention multi-stage outlet that has a more moderately sized pipe. And then this could be the outlet structure, maybe something that has an open top with different levels of weirs. Or in some cases, it may be actually more like a traditional area intake that has openings on the sides that control the water level. So the water level rises to a point with these moderate storms, but then eventually it flows into the openings as the water level rises. For extended dry detention, you may need to reduce the release rates even further. In the example we worked, if you're talking about maybe a 9-inch or opening or orifice, so maybe there's a 12-inch pipe here with a cap and a 9-inch opening. Maybe you have for some really small sites where the release rates get really low, maybe you have a perforated riser that helps screen out some of the trash and garbage so that this outlet doesn't get clogged, because some of these outlets could get as small as 3 or 4 inches. We don't require them to be any smaller than 3 inches, but you may need some sort of provision on the opening for those smaller ones to make sure that debris doesn't get in there and clog it more frequently. And again, this could be an inlet with an open top and a grate, or it could be an area intake with just openings on the sides to control the big storms. So as that water level rises, then it flows into the structure. So just kind of simulate how this works. We've got these different stages, the small to handle the small storms, and then it fills up and it starts to activate more and more levels. Um, Finally, it starts to, at some point, like the actual outflow pipe itself, it becomes the capacity limitation. And then you're always going to have, you always want to make sure that you have a good emergency spillway. You know where that water is going if the basin gets full. So before the storm, your basin may be dry, or maybe if there's a pond, maybe that water level depth goes down like that. As the rain comes in, it fills up to that first level. You want to make sure your second stage is above the high water of your 1 year storm, so that make sure that all the water is going through that first stage during those smaller events. Then as water levels rise, it starts to activate more and more of these outlets. So similarly with a wet pond, in some cases we actually have these set below the water level. So the water level gets drawn out through here. And then we'll set a water level control structure with stop logs that actually controls the water level of the pond. So the water level, we draw out some of the cooler water. We're leaving more of the better oxygenated water in the pond for the pond health. But again, we can manipulate that water level in the pond with the stop logs. If you need to draw the water level down for maintenance or initial seeding, you can pull a few logs out, or you can reinstall them when that's complete. So different variations, different ways to do these water level control structures. There's our multi-stage outlet structures. There's not one kind of a one size fits all approach. Here's a close-up of what that water level control structures will look like. This is something you could design yourself. It could be something that's, custom, that's built on the project. I tend to like specifying. There's a company out of Adair called AgriDrain that produces these. Those have been they're relatively inexpensive and pretty easy to use, but you certainly could use a different manufacturer or design them kind of yourself. The main thing is to pick one that where these stop logs are going to seal really good and not leak, um, because you want to make sure to hold the water level at the appropriate elevation. So they usually require kind of a track with a gasket, and they're usually oiled up to get a good seal. Here's just some real world kind of pictures of how this can be applied. This was an during construction photos, so they did come back later and cut these cleanouts down to an appropriate elevation. But this was a bioretention cell, so it's basically a dry detention basin that also has a bioretention cell in the bottom of it to provide for water quality. Um, the outlet you can see over here. So the under drains tie into that structure below the grade, but then it's kind of hard to see in this photo. I'll zoom in a little bit. There is a small pipe that comes out about 6 to 9 inches above the bottom of the bioretention cell that goes into the structure here. That's our channel protection volume control. And then there was a cut opening on this face of the inlet here, and then water can spill over the sides if the water level rises about another foot. So there's actually a grate in that structure. Fortunately, I didn't have a closer picture of that one. I'll have to go out and take one. And here you can see the auxiliary spillway um, in that area. So that was a new construction. These can also be retrofit into existing ponds and detention basins. This is Glendale Cemetery here in Des Moines. They did a retrofit. They wanted to do some dredging, but they also wanted to apply a water quality component to this pond. The old pond outlet, as the water level rise, we just kind of let it out as fast as the pipe would allow it to go. We provided a kind of a low flow stage, so you can see the Hickenbottom. It's for trash. Then it goes into the water level control structure. This ties into a storm sewer that runs parallel to the pond over on this side. Here's what that inside of that AgriDrain water level control structure looks like. This little handle here is the actual operator that you can pull out and use to grab the little hooks on the stop logs and pull them in and out to manipulate the water level to whatever combination you want. And then this is the outlet structure. There was an existing structure there, so we basically just had them cast a little higher wall around a couple of the sides, and then install a new grate here that's on an angle. Here's a picture of that grate. And one reason why we placed it at an angle instead of flat is if you start to have debris, the debris will collect on the low side of the grate. So as the water level drops, it'll settle there where you can clean it out. Where if it was placed absolutely flat, it could create a mat which could block flow across the inlet. And you can see here we actually cast a little lip in front of this. So this is forcing the water level to rise to the desired level. So water actually has to flow to that other inlet I showed you previously to go out during the small storm events. But then in this case, this was a water quality volume retrofit. So once the water quality volume storm event happens, then the water level will start to crest over and spill into the inlet that way. So they didn't have enough space at this one to do the complete channel protection volume storm, but they were able to provide extended detention for the water quality event instead. Oops. And then last, just to kind of wrap up, and then we'll be glad to kind of have some discussions and questions. This was a during construction photo, so apologize for some of the lack of erosion and sediment control in this photo. But this was the dry basin on a park project. And again, just showing that kind of outlet, small storm outlet here with a little trash guard on it. And then there is a water level control structure here that handles control from an under drain. And this was an existing structure that was in place. So instead of having an open top, it's just kind of more traditional area intake. There's another one on site that only has the upper openings. This one had both a lower and an upper opening that was designed to control the more moderate and large storm events. So, you know, the 1 year high water level doesn't get above this lower opening. Once it got above that level, it could start to access that lower opening. And when the level got up to about the 25 or 50-year storm, then it started to access these upper openings and allow flow into that. So that was the quick tour I had of unified sizing criteria and multi-stage outlet design. We've left time for some questions, so I'd be glad to accommodate any just questions or discussion that might be out there.
Thanks, Greg. If anyone has questions, please type them in the chat and I'll be happy to share. Don't have any right now, but we'll give it a couple seconds to see if anyone has questions. In the meantime, I do want to thank everyone for attending today. I'm going to share this recording on the Rain Campaign YouTube page. If you can't find it, just email me and I'll be happy to send you that link. Isaac wants to know where the biocell basin is located.
The one from the presentation is actually at Southeast Polk High School over in Pleasant Hill. It was it was installed just this year as part of a new maintenance building that they have on site.
All right. Well, I'm not seeing any more questions at this time. Thank you so much, Greg. And I will send out an email about next month's Lunch and Learn shortly. So thanks, everyone.